All right, so yesterday, here's where we left off, right? Yesterday we were in the process of doing this with some help from technology, correct? Okay, so bust out your TI-84s. Okay, and you should be able to just go in and pick up where you left off, right? So we got to go to get to the matrix screen. We hit second, and then that button right there I'm pointing at.
To the power of -1.
Yes, because when you hit second, then it defaults to the features that are above the keys, right? Okay. So we're in the matrix screen. We got to go over to the edit menu. And we're going to edit matrix 1, and there it is, right? It's a 3x4, and the way to enter these, now, it's rather than, I'll give you a little advice with this, rather than trying to use the left and right arrows, the best way to do it is just to always hit the enter key, and that's going to run you through like you're reading a book. So it's going to go from left to right across each row. And so there's our, we agreed, right, from yesterday that this first equation, the coefficients are just 1, 1, 1, and 78, right? Yes. So there's row 1 corresponds to equation 1. There it is. Okay, now down to equation 2. First coefficient, 0.05. Oops, I think I messed that up. 0.05.
What?
Right? Because look, I'm down to equation number 2 now.
Wait.
So I'm on row 2 in my 3x4 matrix. Okay. Well, I mean, you probably do too. If you don't, row 1 is just going to consist of the entries in the matrix for row 1 are just 1, 1, 1, 78.
Mine just had 3 showing, so it's easier where you put them.
Okay, right, and so your matrix needs to, okay, and then, right, sometimes it'll do that, and you just gotta go all the way over to the left to see the whole thing. There you go. Okay, and then if you hit enter again from 78, it conveniently wraps right around like you're reading a book to the next line. Okay, so then we'd enter 0.05, enter, and then we'd go 0.1, enter, and then we'd go 0.25, enter, and then we'd go 12.4. Whoops. Right, we good? Okay. Now for row 3, we'd go 0.05, enter, 0.1, enter, 0.5, enter, 22.15, enter. Okay, and now we got our whole matrix in there. Everybody agree?
Yes.
Okay, now if we were to go, let's go ahead and exit. So we'll go second, quit. Now I'll just show you something. If I go back into the matrix menu, so if I go second, matrix, and now I'm on names, so if I just hit enter or 1, it pulls up that's the symbol for matrix A. Okay, and if I hit enter, look what it does. Okay, it gives me back the matrix that I just built, and that fits our system, correct?
Yes.
Okay, so now that we've done that, what we want to do with this, here's how we can solve this system. This is really cool, but it's not going to make, like I say, I'm just going to kind of show you what buttons to push for now. At the end of the year, maybe we'll have a chance, we'll talk about why this works the way it does. We're going to go into, question?
Is on the bottom equation, or like the bottom set, is it supposed to be 0.25 too?
No, it's 0.5. Remember, because we
doubled it.
we doubled the number of quarters in that one, okay?
How do you get out?
You just hit second quit up at the top.
And then you just press clear then, right? Is that what you did?
Then, and I just cleared I just cleared the stuff off my screen. Okay, so now we're going to go into the matrix menu again. So we go second, matrix screen, excuse me. We're going to go over to in the matrix screen, we'll go to the math menu. And now watch closely here. We're going to go all the way down the math menu until we get to something called reduced row echelon form. The quickest way to get there, honestly, I'll just show you. Go to the math menu, and it's near the bottom. So if you scroll up, it's quicker to get there, right? It kind of wraps around from the bottom of the menu and you can go up to B, okay? So we want reduced row echelon form of matrix A. So then I'm gonna go second matrix and I'm gonna choose either 1 or enter. And I got matrix A and I'll close my parentheses,
Oh, shoot.
okay? I'll pause there.
Oh.
Everybody, so I'll pause there for a second. Everybody see where we are? Want me to do it again?
Yeah.
Okay, let me do it again. So let me clear that and I'll do it again. If you already got it, you're fine, but if you didn't, watch again. So we're gonna go, with nothing on the screen, we're gonna go into the matrix screen and go to the math menu, the middle one. So scoot to the right. And we're just gonna scroll up from the bottom until we get to RREF. That stands for reduced row echelon form, which doesn't mean anything to you now. Okay, and we're gonna choose that. Everybody with me? And it gives me, okay, it gives me this. Now, anytime on the calculator, everybody look at me for a second. Anytime on the calculator where you do something on the TI-84, where it opens a set of parentheses, then that just means it's expecting you to put something in there, right? It's a function, essentially, right? It's doing reduced row echelon form to something. So I gotta put something in the parentheses so it can do it to something. We wanna do it to matrix A, the matrix that we built, the 3x4 matrix. And so I have to grab that though. So to get there, I go second, matrix, and then in the first column, I would just either hit a 1 or an enter, and it's gonna grab the matrix A that we built, okay? Now I close the parentheses, so it's inside, I'm doing reduced row echelon form to whatever's inside the parentheses, which is matrix A. Now here's the magic. If I hit enter, look what it does. Okay, this is pretty cool. So what this did is it did a whole bunch of matrix operations, and think what these equations are telling me. The first column were the coefficients of n, correct? So think what that first equation is saying. It's saying 1 times n plus 0 times d plus 0 times q, which is just n, right? So n equals 25. So there's 25 nickels. How about that? The second row is telling us that 1 times d equals 14, so there's 14 dimes. And the last row is telling us 1 times q equals 39, so there's 39 quarters. Yes, sir.
Would this work with, like, 2 variable equations?
Yes, it would. This would work with 2 variable equations as well. Yeah, so I mean, you could do, like, if you wanted to solve a 2x2 matrix, you would just have, you start with a 2x3, right? If you had a 2x2 system, you'd make a 2x3 matrix. So you could have like a column for x and a column for y and a column for the answer, right, for the constant. Make sense? Okay, so you could. However, for a 2x2 system, it'd be easier, probably just in Desmos, just to graph the 2 equations and find the intersection, right? Okay, but you can't graph 3x3, right? I mean, you can't graph a 3-dimensional object, right? So it's finding those intersections in space is a little tougher to do. You need to have some kind of a weird screen that was 3-dimensional, right? So here, that's where you need matrices. Now, the nice thing about this is, though, what if you had a system, and you might, I mean, in some situations, you might end up with like a 9x9 linear system, where you've got 9 unknowns and 9 pieces of information. That can happen. Now, doing it the old-fashioned way, like by using matrix math, I mean, you could do it with matrices relatively quickly. Might take you 20 minutes or something. You know, set up the matrices and do all the operations. To do that without matrices, like, you know how we did that actually algebraically solved the 3x3 system? Now just think what would be involved in solving a 9x9 system. Right? In a 9x9 system, just think what that would involve. You'd have to collapse that into a couple of 8x8 systems, right? By eliminating the same variable. Each of those 8x8 systems, then, you'd have to collapse those into 7x7 systems. Can you imagine? That would take you probably 6-10 hours. I've never, yeah,
That would
probably.
be really satisfying though to get an answer.
It would be.
Yeah, it
But that would-
unless you made even one mistake.
Okay, but you see my point? I mean, that would take you, to do that algebraically, that would be a long, arduous process. That would probably be, I mean, how many pages of work would that be?
What if it was like the one?
30, 40 pages of just nothing but, yeah. Okay, okay, but now hold on. So if I wanted to do a 9x9 system with matrices, That's no big deal. I just make a 9 by 10 matrix and plug in the numbers and hit go, and it's gonna tell me the answers, right? So can you see that this is, a hugely valuable thing to be able to do, right? Now, there are some, okay, so everybody, you kind of got, I've got a video made. You can go back and reference the video if you forget what buttons to push, right? But you can check your answers this way. On the test that we're gonna do, would you like to do, I mean, maybe, I don't know,
Let's do it 9 by 9.
I'll add one on there. I'll give you a 4 by 4 maybe. But I'll put a section on the test where you can use your graphing calculators. At the very, like, oh, does that sound good? At the very end?
Yeah.
And I'll let you just do this one. It's a free, I mean, like, it's good to know how to do. It'll force you to know how to do it, and it's a free answer, right? I mean, it's, as long as you can do it, you're gonna get one right on the test. Yep.
Will you always use the RREF?
There's another way to do it, but this is the best by far. You can do it using matrices and inverse matrices, but I'll show you why this one is so good here in a second. So let's go on with our stuff from yesterday. I want to wrap it up. I'm going to get rid of this for a moment. So, oops, that's not what I wanted. I want to go back to.
I think you passed it on accident.
Well, I want to pull up an example. I thought I had one. Maybe I
The
didn't.
one from yesterday with the nickel starters and
Um,
Think about it.
Okay, well, I'll make it. It's just to get it out of my face.
that is
But first, Courtney has a Courtney, why did you make it from the?
No, I didn't really.
I just my way, because I'm testing my father so that she. Well, but it's down here. But Courtney had it where she was very tight and she all the time. And then all this hair until it really wasn't super. Like, you're doing the. Well, you told me to sit right here.
We're not gonna do any of it.
Okay, here we go. So let's look at this one. How about? Let's go through and let's do this one algebraically first.
This one's not on our notes anymore.
This one is not in your notes. No, this is one, like, this is kind of beyond the notes. This is going to be one that doesn't work normally. This wouldn't be in a regular algebra 2 class. So what's going to be the variable that we'd probably choose to get rid of here?
Ooh, a 5.
Let's slow down.
Let's get rid of Y.
Y for sure, right? We want to get rid of Y because Y is easy to do. Look, if we call this system A, I can get rid of the Y's. And what if I called this system B? I can get rid of the Y's without doing anything.
You put this one on.
Yeah. Okay, so we can just skip a step here. If I just combine system A, we just do that, right? So we add those up. What do we get?
4x plus 4z.
Hang on.
8x.
Right?
Plus 8.
So if I add those up,
Equals 16.
Skipping that.
I'm going to get 8x plus 8z equals 16. Good? Everybody agree?
Yeah.
If I combine system B, I'm going to get negative 6x minus 6z
Equals negative 12.
equals negative 12. There we go.
Oh, I see it, yeah.
You see it?
I just.
Okay, so we could make these a little bit simpler, right? Like I could take, I want to show you something here. This is just a linear equation, right?
Yes.
So let's take the red equation. What could I do to both sides to make that simpler?
Divide by 8.
Divide by 8. So I could turn this into, whoops, wrong color. I could turn this one into x, I don't know what that was,
The most beautiful x I've ever seen.
x plus z equals 2. And I can turn this into I could divide both sides by
-6.
-6, right?
And x plus z equals
And I'd get x plus z equals 2. Okay?
So it's independent.
Okay, so if I were to combine these two systems and subtract them, I'm gonna get 0 equals 0, right?
Which
So
means
it's infinite.
infinite.
Infinite. Okay, so that means this would be a case where there would be, the planes are overlapping in a way, like, for example, maybe it's something like, I've got this plane and that plane, and then another one coming through at a weird angle. So they're intersecting in a line, maybe. The joint, the point of, the area of intersection, instead of being a point, is a line, and so there's an infinite number of solutions, right? Okay, so that's how we would, when we combine these, we're gonna get something like, I'll just show you.
So would no solution be if it was parallel?
No solution's gonna be if they're all parallel, exactly. So in this case, I'm gonna get 0 equals 0, which is true. And so we know that we've got an infinite number of solutions of some kind, okay? It's a little more complicated though, and if you think about this compared to a 2x2 system, if we get an infinite number of solutions, there's only one possible thing that could be going on if we've got two lines. And what is that? They're the same line, right? So there's really only one thing. Now, there's a whole bunch of different things that could be going on here. It could be a line, it could be all three are the same plane, right? There's a variety of different things that could be happening here. Not a ton, but there's more than one thing. Let's look at another example. How about this one? Same kind of thing. So once again, I'll probably get rid of, well, actually, no, what's going to look like here? Probably the,
Do I have to write this one down?
it'll be on, the notes will be, I'll publish the notes. If you don't want to, you don't have to. Maybe the, I don't know, the Y's, I guess, probably, huh? Probably the Y's again. So let's make this system A. And probably, like, this would be a good system B, wouldn't it? Something like that? Okay, so system A is going to become, let me just write it down, 3x minus 3y plus 2z equals 0, and 4x plus 2y, minus 3z equals negative 14. So what do I have to get rid of the y's? What would I need to do? Okay, good. Top by 2, bottom by 3. And that would give me 6x minus 6y plus 4z equals 0. And,
2 times 0 is 0.
Oh. Corey?
whoops, and then the bottom one would be 12x plus 6y minus 9z equals negative 42. Everybody agree? Yeah. Add them up, the y's go away. I get 18x minus 5z equals negative 42. Everybody agree? Okay, over here. So on this side, we're starting off with 4x plus 2y minus 3z equals negative 14, and 20x plus 10y minus 15z equals negative 42. What do I have to do? Top by negative 5, okay.
Oh, wait.
Because we got to get the y's to go, right?
Yeah.
So that's going to give us negative 20x, minus 10y plus 15z equals negative 70, or positive 70. On the bottom, we get our 20x plus 10y minus 15z equals negative 42. Yeah, I add those up, and
They cancel.
look what happens here.
They-
So those cancel, and those cancel, right? And so I get the solution here. I get the solution 0 equals
Okay, or 28.
28.
Yeah.
Yeah.
Okay, and if I mean, I'm stuck then, right?
Yeah.
So this thing already collapsed. It could have collapsed there, or it could have collapsed here, but it was gonna collapse at some point, right? And so,
Why don't you just put like doesn't equal to correct it, so you don't.
okay, now hold on here. So really, these two probably weren't good ones to use, because look, this bottom one is it's just gonna be a multiple of the top one, right?
Yeah.
Okay, so what if we, instead of using those for B, we would have, I mean, for reasons I don't want to go into, we would have known right away this wasn't going to work because of that. But let's pretend we pick different ones here. I want you to see how this, I want you to see this a little different. So what if we pick, for system B, let's say we picked these two instead. Okay, so you're going to see essentially the same thing happen, I guarantee. So you're going to get 3x minus 3y plus 2z equals 0, and 20x plus 10y minus 15z equals negative 42. This is a little tougher. I got to multiply the top one by 10, bottom one by 3.
Yeah.
Okay. And we're going to get 30x minus 30y plus 20z equals 0, 60x plus 30y minus 45z equals negative 126. Add those up, the y's go away, so I'm going to get 90x minus 15z equals negative 126. Now if I combine these two,
Wait, is it 25?
did I mess that up? 25, you're right, yep. Okay, good. Now if I combine these into a 2 by 2 system, I get 18x minus 5z equals negative 42, and 90x minus 25z equals negative 126. So I could just multiply the top one by negative 5. And how about if I just drop that one down there? Then we can line those two up.
Yeah.
Okay, so I get negative 90x plus 25z equals positive 130. So look what happens. Those cancel, so I get 0. 0 equals 4. That's false, right? So once again, we see that this one has got no solution. So this has to be 3 parallel planes. Okay, now here's the really slick thing.
Oh, wait, what? It has to be 3 parallel, oh, done.
Has to be,
Okay, done.
right, has to be. Well,
They were never-
actually, that's not true. That's not true. I spoke too soon. It could be 3 parallel planes, or it could be like 2 parallel planes, like it could be the floor and the ceiling in this wall, because there's no common intersection. Right. So at least,
So the 3 parallel is still.
right.
Okay.
That would be one possibility. Or it could be like, it could be 3 planes that are coming at you that form a triangle, if you look down, right?
Oh,
They-
because it's like 2.
Right, because all 3
But
planes
not all
never
three.
intersect in one place, right? As long as all 3 planes never intersect in one place, then that's an okay solution. Now, here's the cool thing about this, though. If you use the reduced row echelon form trick that I showed you, you can actually tell what's going on. This is what's really amazing. And this is a little bit high level. You're not going to get this completely, but you'll at least appreciate how cool this is. And when you do this eventually in your math careers, you'll remember back to Mr. Roy showing this to you. So, okay. So if we pull up the calculators, let's go change.
Some stupid answer to do.
So here's the first one we did.
Oh,
Okay, there's our system, right?
is this A or B?
This is the first one we did that was infinitely many solutions, right? Okay. So let's see what's going on. If I pull up the calculator, and let's just go in and change our matrix. Let's just alter the first one. So we'll go into, we'll clear this all out of there. We'll go into matrix edit, and we'll just edit matrix A to match this one, right? So it's a 3 by 4. First row is going to be what? 4, 2, 4, 14.
Yeah.
Second one is 4, negative 2. Whoops, can't do that. I think I have to use the negative thing on here. Negative 2, 4, 2, right?
Yep.
That's row 2. Row 3, these are all in standard form, so I can go negative 10, negative 2, negative 10, negative 26, right? Okay, we good?
Yep. Yeah.
Okay, now we're going to exit, right? So we'll quit. Now what?
Math. Or you go to the
Okay, matrix, math,
then B.
RREF,
Whoa, that's
Then second.
matrix A. Okay, now watch this. Okay, look what this is telling us. Okay, this told us, so here's how you can tell immediately that this does not have a single solution, because if you cover up the last column, it doesn't look like what's called an identity matrix. The identity matrix is the one that has the diagonal descending from the upper left to the bottom right would be ones and everything else would be zeros, right? And here's, that's the matrix equivalent of the number 1. And here's why, because think what it did. It told us that the value of x was equal to something, the value of y was equal to something, and the value of z was equal to something. This is telling us something very different, right? This is telling us that x plus z equals 2 and y equals 3, and this bottom row down here, this is the important one. Look what it says. It says 0 equals 0. 0 equals 0 is true or false?
True.
It's true. Okay, so when you, here's kind of the steps you go through. When you do the reduced row echelon form, if you don't get a normal answer, right, which is like the last one, which is just ones, you know, all zeros in a diagonal of ones, and then your answers, you look at the bottom row. If the bottom row is all zeros, then it means infinitely many solutions, right? Because it's a true statement. It says 0 equals 0, right? It tells you a little more information about that, though. It's an infinite number of solutions, but the nature of those solutions is this. It's that x plus z has to equal 2, so that's telling us something in 3 space. That's going to tell us the equation of a line in 3 space, okay? That sits in the y plane, when y is 0, so it sits in the xz plane. So it's going to be that along with y equals 3. The combination of those two linear equations is going to tell us what the intersection looks like, that's beyond the scope of our class right now, but that carries some important information. You get what I'm saying? It tells us how is it infinitely many solutions, right? That's how. That's the intersection. Okay, yes?
Okay, so if you got something stupid like that kind of, but the last one, it was 0 equals something like 1 or
Okay.
greater than 1, that would be not true.
Then, right, okay, so let's look at one like that. Okay,
Like
so
the
this
last
is one where, and for this point for us, I mean, like for you guys, really the main thing would just be, this would be, you look at that bottom row, and because it's all zeros, you would know this is one that's all reals, right? There's, or not all reals, infinite number of solutions, infinite solution set. Okay, let's go back and let's look at another one of these. So now let's look at the second example that we did that ended up being false. So let's clear this one out of there. We'll go back and go matrix, edit. We'll edit matrix A. And so what's this one going to be? We're going to have That's supposed to be a 3. That's a -3. You read them off to me. -3, what's next? 2,
Oh,
0.
Four,
Oh, it only goes to I.
2, -3,
Oh, no, it only goes to J.
14.
Oh, 14.
As far as it goes. So to answer your question, no.
Here, Grayson, you read them off to me. Just one person so I can get them. What's the next one? 20,
10,
10,
-15,
-15,
-42.
-42. Okay, there we go. So there's our next matrix. So we'll quit. We'll go second, matrix, math, reduced row echelon form, second, matrix, A, close parentheses. Okay, what do we get? Now,
That's how you know it's no
okay, here's one thing that's kind of nice though. When you see those big decimals, there's another great trick. Watch this. We'll go math, convert to fraction. That's a little better, right? So what's this tell us? Bottom row tells us 0 equals 1. That's false, right? So there are no common intersections. So this stuff up here is not really telling us anything too meaningful, right? It's telling us, in fact, I'm not even sure how you'd interpret that, but the bottom row is just telling us there is no solution to this. There's no place where all 3 planes intersect. Okay? Make
So
sense?
if it's 3 zeros, there's no solution.
So if there's 3, well, look what that says. 0x plus 0y plus 0z equals 1. That's saying 0 equals 1. So that's false, right? Okay. All right, so that's matrices in a nutshell.
That's a good warm-up.
Yes. Okay, so now, just for the last part of today, we're not going to have a ton of time, but I want to just introduce you to something, because this stuff you already know, and we'll pick this up tomorrow. What do we have? 8 minutes, okay. So, inequalities, right? I want to just make a point. So whenever we talk about an equation, don't lose sight of what a solution to an equation means, right? Like if I've got a linear equation, like let's just throw up, for example, something like this, right? Here's a linear equation in standard form. Like if I have 2x plus 3y equals, what's it gonna be? 17. Okay, what's it mean to be a solution of this equation?
Coordinate pair.
Okay, it's gonna have to be an ordered pair, right? Because I've got x's and y's, and what does that ordered pair have to do?
Has to add up to be 17.
Say it
Add
again.
the 2 points together would have
Well,
to equal 17.
Okay, in other words, it has to satisfy this equation, right? So for an ordered pair to be a solution, when I plug those values of x and y in, they have to make this a true statement, meaning they satisfy the equation. How many points are there in the xy plane that do that?
One.
How many points are there? When I say a point in this case, a point is just, like an ordered pair is a pair of x and y coordinates, right? A point is just the graph of that ordered pair, okay? So how many solutions, we'll say that at first, how many solutions are there to this?
2.
Those are all partially correct.
Infinite.
Infinite is correct. Infinite is correct, and we can find a bunch of them, right? Like if I want to find a solution to this, I could do something like I could say, well, okay, we'll find an ordered pair that works. Let's find the one where x is 0. When x is 0, what would y have to be?
Some stupid number.
But as a fraction, it would be
17.
17 thirds. So there's a solution, right? That corresponds to a point in the xy plane, doesn't it? Okay, let's find another one. How about when y equals 0? X would equal 17 halves. Okay, in fact, I could do this for any number. Like I could pick, what if x is 4? Then that would give me 8, right? I'd get 8 plus 3y equals 17. Subtract 8 from both sides, I'd get 3y equals 9. So y would equal 3. We found 3 of them, right? there's an infinite number of them, what would the graph of that infinite set of solutions look like? A line. What do you know? And every point on that line, the coordinates corresponding to the point on that line would constitute a solution to the equation, right? Okay, you get the idea? Okay. Isn't it, like in math, this is what's really good about it, and that's especially like in an honors level class. It gives you the opportunity to go through this stuff deeply enough to kind of get an appreciation for, yeah, I've been doing all the algebra, but then look how this all comes together, right? It's also self-consistent, right? So now, how does that change when we talk about an inequality? An inequality is just like an equation, only the relationship is a little bit different, right? So instead of saying y is equal to negative 2x plus 9, now we've got the inequality y has to be greater than or equal to negative 2x plus 9. Just like before, I'm going to get an infinite number of solutions to this, but the solutions are going to, the set of all the solutions is just going to consist of every ordered pair that's going to make that a true inequality this time, that will satisfy the inequality, right? So we could check these, for example. I could check 7, 4 and see if it works. If it makes that true, then it's a solution, right? So if I plug, so let's just try it and see. If I plug 7 in for x and 4 in for y, we're going to get 4 is greater than or equal to, and I'm going to put a question mark above it because we don't know if this is true. We're checking it, right? 4 is greater than or equal to negative 2 times 7 plus 9. Let's see if that's true. Is 4 greater than or equal to negative 14 plus 9 is negative 5?
Yes.
True or false? Yeah, it is, isn't it?
Oh,
Right? 4, that is a true statement. So this is an example of a solution. See what I'm saying? Okay? So then tomorrow, what we want to do is we want to come in and we want to see if we want to approach this in a couple of ways. The first thing we want to do is we want to see what a graph of that solution set might look like. Instead of it being a line in this case, you remember what it's going to look like?
A weird shape.
It's going to have a boundary line, and it's going to be a shaded, it's going to be a half plane. It's going to be the entire infinite half plane either above the line or below the line.
I remember those.
Okay?
those,
So we'll do it tomorrow.
Wait, come on, Marty. Are we gonna have any better anything posted tomorrow? Because Nancy's leaving at 8.